Welcome to the course on Introduction to Electrical Engineering, lab lecture 27 today on digital circuit part 3. We will start from outline, starting from introduction, then we will talk about sum of product, that in short we call it SOP, and PO, product of sum, that called POS, and well we will like to discuss about simplifying logical methods in of course digital circuits like by Venn diagram method, and we call it Karnatak Map method. And then we will like to talk today combinational logic circuit with the example of half adder and full adder by half subtractor and full subtractor, then comparator circuit. Then we will like to of course discuss the application for multiplexer circuit and demultiplexer circuit, followed by exercises and numerical problems, followed by references. So, now coming as a recap of various logic gate, which we already discussed it in the last couple of lectures. So, first we call it like only the yes, I mean the input go as the same output, and this we normally use as a called buffer, we already discussed many times. And of the another gate with single input gate is normally we call it NOT gate. So, is given like input A, if it is 0 then low, then output is high, and if input is high then output is low, then followed by the AND gate, 2 input AND gate. It of course can be multiple input AND gate, we have given an example also multiple input AND gate also, then OR gate, exclusive OR gate, NAND gate, NOR gate, and exclusive NOR gate. So, these are the typically kind of like a 8 kind of logic gates which are used normally for realizing the, you can call it like a typically many digital circuits, I mean we design based on that, and even the any expression or many applications we realize with the help of these logic gates. Of course, how we reduce the typically number of the gates and hardware, we have the method we will like to discuss today on that. Like, so, now coming to the law of rules for this combinational logic. So, the law of linear algebra is plus, which denoted by R or, and the A B denoted by A and B, and cumulative rules which we call it A plus B equal to B plus A, and well another is A B equal to B A. Then we have associative rule, we already discussed it. So, A plus in bracket B plus C will be equal to in bracket A plus B plus C, and similarly for and it will be A in bracket B C will be equal to in bracket A B to C. Then we have a distributive rule where we call it A plus B C equal to A B multiplied in bracket A C, and A plus A B equal to A. Similarly, for this another one A into in bracket B C will be equal to A B plus A C, and A in bracket A B will be equal to A. Then we have of course, the interesting algorithm De Morgan theorem, which is very important theorem and law for here. So, that is A dot B dot C whole bar equal to A bar plus B bar plus C bar, and similarly A bar dot B bar dot C bar equal to A plus B plus C whole bar. So, this we call 2 theorem De Morgan laws or De Morgan theorems like on. Now, coming to the introduction for this typically of a scope of digital technology and digital electronic circuits extend to many domains such as software, healthcare, automation and business etc., and combination logic circuits are the basic building block of digital system, and they are used in various applications as digital measuring technique, digital processing, industrial processing, then computers, calculators, then digital communication. Now, coming application typically you can think about it like a medical imaging system, then your 7 segment display, I mean which are used for with the help of LED for many purpose, like I mean in different places you might have seen that LED display. Then your typical example is using exclusive logic based staircase wiring system, and you can see how it is the wiring that you have a 1 and 2 on top and bottom, and 1 is connected with the supply and 2 is connected typically I mean with the through the bulb it is connected to the 2, and now there are 2 switch on you can call lower floor and as well as upper floor, and then the position of the C switch can be 1 on 2 of both the C switches can be on 1 and 2 lower as well as upper, and then you can switch on or off either from bottom switch or top switch typically in this, and this we call it exclusive or logic based stair wiring. So, this is a very good example you can call it of XOR logic gate in this staircase wiring system for the lighting, or especially for use normally for purpose of lighting or for many other appliances which you can switch on from upper floor to let us say lower floor or lower floor to upper floor like. Then typically multiplexer and demultiplexers, they are used in typically in many system, as you can see the photograph. Then we have a typical example of this multiplexers as a selector in combinational logic circuit, that you can mux the many input starting like MP3 player or laptop sound card, or you can have a digital satellite or digital cable camera. You can have a multiple sources connect to mux, and your surround sound system can be can be connected to any one of the let us say 4 devices. So, even by using a 2 selector switch, you can have a typically any one of these device connected to sound system, or you can probably use the sound system for any one of the 2 at a one at a time like. So, this is a good example of multiplexer system like. Similarly, we can have a typically your single source like laptop can be connected to many output system, which again we call it throw selector, and this we call it certainly demultiplexer combinational logic system. It can be either you can connect to Bluetooth speaker or fax machine, printer, smartphone, many output devices you can connect a single source like your laptop. This is an example of demultiplexer. Then we have a typical example of encoder, that you have a LED light and it goes to the typically your photo sensor, and then you have a squaring circuit which gives the signal at the output by digital signal processing like. So, this disc with this LED give you the position of the rotor, different position of the rotor, and normally used in different kind of electric motors for the position sensing. Maybe like a stepper motor, your permanent PMSM, many electric motor will require position sensing for control, precise position sensing for the control. So, for that purpose we use typically this kind of encoder system for digital logic, or quadrature decoder, as you can just see here in the typically in photograph, and or your LM393 DIP 8-bit low power voltage comparator IC chip, that used typically for comparing the voltage. And then you have a like a telecommunication network, again connected with the different mux and internet, or through internet if you want to connect all the devices, like maybe your domain data servers, typically the server, many servers and Wi-Fi router, then with the typically firewall several PCs as well as the printers connected through this LAN network or through internet like. Or then programmable logic devices used for many process. So, typically these are the some of the application. Now, we will like to talk about how we can typically use the way of designing these digital logic circuits with the help of some of the concept, like one concept is sum of the product, and this sum of the product you can call it is a canonical form of Boolean expression. So, a binary variable may appear either in its normal form or its complementary form. Complementary form normally you call it x dash if normal variable is x, and consider two binary variable x and y combined with AND operation. So, there are 4 possible combination, and which are as x y, x dash y dash, x dash y, x y dash and x y. These are the 4 possible combination for variable as well as the complement and with the AND operations like, and which we call it min term. So, these we call it the min term. Then similarly, we in the similar manner we have a n variable forming an odd term, which each variable being primed and unprimed called like x dash plus y dash, x dash plus y, x plus y dash and x plus y. So, all are in the parenthesis. So, this we call it max term like with the plus sign. So, that is with the representing the OR operation of the logic gate like. So, these we call it the max term, and n variable can combine to form 2 to n min term like. So, the various possible standard product and terms are called min term, and with the standard sum or OR called max term. So, n input variables which can call it bits can be combined to form 2n mid term and 2n max term designated by their decimal equivalents. Bits are assigned values such that each mid term yields value 1, while each max term yields the value 0. So, the typical example here with the 3 variables input here x, y, z, and each max term is a complement inverse of the corresponding mid term. So, you can call it m I equal to m I dash, that is complement of your max term and corresponding to De Morgan laws, and you can see there are typically 8 possible combinations for mid term. I mean min term is when there is a 0 you represent the bar, and when it is a 1 you would use the variable as it is. So, you can see all 8 mid term and designated m 0 to m 7. Similarly, all max term are represented by plus. So, you say typically you can call it here I mean like x plus y plus z, they are just inverse of it. So, m 0 and last one is all 1. So, it is called x bar plus y bar plus z bar, that is m 7. So, these are m is the capital m represented by max term which yields 0. So, we can have a example here, we can write the expression for the function f using the truth table. I mean this is a truth table, we can say x, y, z are the possible combination 2 to the power 8, and this we can see we have only output under certain circumstances for a particular logic. So, we have a f only when your 0 0 1 combination and 1 0 0 and then all triple 1, that is the 1, and this can be represented as a sum of product using the midterm called and collect all the function which term f equal to 1. So, we will take only the 3 combinations, these are the 3 you can call it the midterm midterm. So, that is f starting from first. So, this x y plus y, this corresponding to this row into z plus the second row, that is your x y bar and z bar, that is corresponding to the third, and third one is x y z, and this we can call it f equal to m 1 plus m 4 plus m 7 corresponding to the location as we can consider corresponding to decimal. So, that is you can call it for this truth table, this function if I have a all 1, this we call it the midterm expression for the function. Similarly, we can have a expression in terms of max term considering all 0. So, which is a you can call product of the sum. So, here you can call it the product of sum is that we will take all the 0 functions. So, here first is the all x plus y plus 0, that is first row, then second is where the 0 is there x y dash z, and similarly like all the 0 we are taking in as a product, and this we can write f equal to m 0, m 2, m 3, m 5, m 0 which consists of all these, and this we call it product of you can call it product of sum, because these are the different product, this is different sum and this is the product, and we call it like a typically expression also we write as a product and this we write as a sum. So, we call it product of sum using max term and the collect all terms which have a f equal to 0. So, any Boolean function can be expressed as a sum of the midterm SOP form or product of max term, that is POS form. So, this you can call it Boolean functions expressed as a sum of product or product of sum are said to be in canonical form, and some of the variables may be missed in canonical form as it is the simplest solution from of truth table, and in standard form the Boolean function will contain all the variables in either true form or complemented form, and example typically are canonical form. You can call it y equal to a plus b bar c, and standard form from the above canonical form can be y equal to a bar b bar c plus a b bar c bar plus a b bar c and plus your a b c bar and plus a b c. So, this represents the typically in canonical form this expression in a standard canonical form, which is a typically considered all the sum of the product, or you can call it the all expression of the min term. So, it is sometimes convenient to express the Boolean function in sum of product min term form, also called sum of AND term, and 2 or more product AND gated term are summed or OR gated to form a Boolean expression, and the typical examples are you can call it a b plus a b c and a b c plus c dash d e plus b bar c d bar, a b plus b c d plus e bar, etc. And the notation for sum of min term is your f is a function of a comma b comma c equal to typically, I mean if you talk about like one sum of is a sum of the product, as you can see here 1 4 5 6 7, and the summation symbol stand for the ORing the term. I mean, this here summation represents the ORing, and dot typically present the OR gated like AND gated. In SOP expression, sum of product expression, a single OR bar denoting inversion cannot extend over more than one variable. For example, there can be a term like A dash, B dash, C dash, but terms like A, B, C bar are not allowed. So, in a standard sum of product expression, each product term contains all the input variable. For example, for 3 input, it will be A B plus A bar, A B bar C is not a standard form. So, where A B C bar plus A B bar C is a standard form. So, now coming to the typically product of sums. So, the 2 or more sum or OR gated terms are taken product and gated to form a Boolean expression, and examples are in bracket A bar B multiplied with in bracket A plus B bar plus C, and similarly for another expression will be like in bracket A plus B plus C multiplied in bracket B bar plus C plus D bar, and another bracket multiplied that C bar plus D multiplied E bar. So, to express the Boolean function as a product of max term, it must first be brought into form of OR terms, and this may be done by using the distributive law, and the typical example of this you can call it x plus y z will be equal to in bracket x plus y multiplied in bracket x plus z. So, a convenient way to express this function is as x f as a function of x comma y comma z equal to pi in bracket 0 comma 2 comma 4 and comma 5. This is typically the again the symbol for multiplication, and that is the reason all these expression is just multiplied from 1 to 2. So, the product symbol pi denotes the ending of max term. So, in the product of sum expression, a single OR bar denoting inversion cannot extend again over more than one variable. For example, there can be term like A bar plus B bar plus C bar, but term like A plus B plus C whole bar are not allowed. So, in a standard product of sum expression, each product term contain all the input variables. For example, for 3 input, it will be like a in bracket A plus B multiplied in bracket A plus B bar plus C is not a standard form. So, where in bracket A plus B plus C bar multiplied in bracket A plus B bar plus C is a standard form. So, now typical example, convert the following Boolean expression in standard form. I mean like A B bar C plus A bar B bar plus A B C bar D. So, the domain of this sum of product expression of A comma B comma C and D take one term at a time. So, first term A bar C is missing variable D or D bar. So, multiply the first term by D plus D bar as follows. So, A B bar C will be equal to A B bar C in bracket D plus D bar, because that will be equal to 1. So, we can multiply it. So, it does not change the value. So, it will be equal to A B bar C D plus A B bar C D bar. So, the second term A bar B bar is missing variable C and C bar and D and D bar. So, first multiply the second term by C plus C bar as follows. So, A bar B bar we multiply equal to A bar B bar in bracket C plus C bar, which that is the value is 1. So, it does not change the value. So, but final expression come A bar B bar C plus A bar B bar C bar, and now the two resulting terms are missing D and D bar. So, we multiply both term D plus D bar as follows. So, we write A bar B bar in bracket D plus D bar, and this A bar B bar C bar multiply D plus D bar. So, then we open this bracket. So, we get A bar B bar C D plus A bar B bar C D bar, A bar B bar C bar D plus A bar B bar C bar D bar. So, this is the final, you can call it in form of sum of product expression for this given example like. So, the third term A B C bar D is already in standard form. So, the complete SOP form of original expression is as A B bar C D plus A B bar C D bar plus A bar B bar C D plus A bar B bar C D bar plus A bar B bar C bar D plus A bar B bar C bar D bar plus A B C bar D. So, that repetitive term is avoided like. So, now another typical example, express f x y plus x bar z in a sum of product form as a product of max term. Product of sum, to convert the given expression into the standard sum of product form. So, that is first we will keep it f equal to x y plus x bar z, and then we have a f equal to typically here x y multiplied z plus z bar, that is have a same value 1. So, it does not make value change, and for second expression x bar z in bracket y plus y bar, and now we open all the expression. So, it becomes like your f equal to x y z plus x y z bar and x bar y z plus x bar y bar z, and this we can call it f equal to the sum of 1 2 3 1 2 6 7 sum of the, you can call it the sum of product like. So, as the product of sum is the complement of the min term. So, it will be like your f dash c will be equal to pi in bracket 0 2 4 5, which are complement of this. I mean, they are missing. So, those 4 are here. So, 4 will be term there. So, in product of sum form, it will be f equal to m 4 m 5 m 0 m 1, and that we can write well f equal to x bar plus y plus z multiplied in bracket x bar plus y plus z bar multiply x plus y plus z and multiply x y bar z. So, now coming to combinational logic circuit. A combination circuit consists of logic gates whose output at any instant of time are determined directly from the present combination of input without regard to previous input. So, here we have input like ABC 3 variable, and here is a combination circuit, and output we have typically output as a x y z, and this circuit by which we are designing it, we call it combinational circuit. So, combinational circuit are consist of like a typically adder, subtractor, converter and encoder, decoder. So, with some example starting which is very commonly used like a half adder and full adders. So, here half adder accept the 2 binary input and 2 binary output. So, the input variables are A and B designate and the augment and this addended bits, and the output variables produce the sum and carry. As you can see here, so input you are adding 2, one is the augment, another is the addended, and here is a half circuit. So, we have a one variable as a output is sum, another is the carry, because sum output will be carry, and this is a functional diagram of half adder. So, now typically this half adder circuit which we are designing here, we have a input A and B and output is a carry as well as the sum. So, 2 binary digits A and B as input, so output sum S and carry C bits. Here we have A and B, typically 2 input have a 4 combination 0 0 0 1 1 0 and 1 1, and the typically sum of this is like a 2 0 will be 0 and then 0 1 sum will be 1 and 1 0 sum will be 1, and when you sum 1 1 the sum will be 0 with the carry of 1. So, now you can form the function corresponding to the sum and carry from this truth table, and the sum will be here typical as an example of here corresponding to the these two terms A dash here into B plus A into B dash. So, for those two condition only sum is there, and this we call it like typically as a represented by exclusive OR, that is the symbol of exclusive OR A exclusive OR B, and typically your carry here C is directly A B. I mean, this is the only here 1. So, this two functions in digital form represents the your half adder sum as well as carry bit, and which can be represented by method 1 by logic gate by method. So, you can have a typically A and B dash and A dash B and you can OR both. So, you will get this function which is sum, and the carry will be just A and B, you use the AND gate and output will be carry. So, this is carry equal to A B. Now, you can have the method 2 using exclusive OR. So, sum is we have already seen sum is exclusive OR. So, you can use directly exclusive OR gate, and this is S, and AND gate you can use for getting the carry. So, this is another representation of this half adder by logic gates for the purpose of designing like. So, half adder accept only 2 input bits. If 2 n bits binary number are to be added, there can be a carry bit in various places also, and full adder makes the provision for a carry in bit, also total 3 input bits, and here you have a like a typically for full adder 2 input and one is the carry in which will be coming from previous side, and you will be having output as a carry output and the sum output like here. And here you can have a kind of a truth table where you have a B and B as input variable and the carry input which is coming from typically from the previous adding, and then you have a carry output and sum of this. So, when you add all 3 including the carry, you will have a sum 0, here carry is there. So, you will get 1 and 1 is there 1 and you have 1 1. So, summation is 0 and carry output 1 and we have a 1 input. So, you have 1, here you have a typically 1 1. So, output sum is 0, but carry will be there, carry output will be there, and you have 1 1, here also 0, carry output will be 1, and when you have all 3 1, you will have a carry also as well as sum out 1. So, these are the 2 output from these 3 input and which you can represent as a sum of the full order by combining these truth table representing the different for S which are having output 1. So, you can have a all mid term here S equal to A dash B dash C I, that is corresponding to 1, and plus A dash B C I, that is corresponding to second, then A B dash C dash, that is corresponding to typically this term because both are bar, and then A B typically C I, and this you can represent taking A dash out here. So, B dash C I and plus B C dash I and plus A B dash C dash plus B C I, and this you can have typically expression as a typically exclusive OR. So, S will be A dash B exclusive OR plus A bar B plus C exclusive bar, and this can be again represented as A exclusive OR B exclusive OR C I, and that represents by exclusive OR gate of 3 input, like that is the full you can call it full adder output like. And then the carryover, carryover is remaining the term where we have a carry here in all 4 terms. So, we can represent this also as a sum of the product. So, CO will be corresponding to like your this term. So, that is A dash B I B C I, A B dash C I and A B C I dash and A B C I, and that can be represented B C I in bracket A plus A bar and A in bracket B C dash plus A B bar C I, and which can be represented as a C 0 equal to B C I plus A with a B exclusive or C I, and this can be B C I as exclusive bar with the ending of with the A. So, this represents this term, and then the second term which you have B C I, that represents the second this expression, and both expression for sum is through OR gate. So, this goes the C output. So, that is output of virtually you can call it carry output like of the full adder. So, that is the way how we represent this full adder by logic gates. There may be many other way also, but this is one of the way to design the full adder. And now, coming to half subtractor and full subtractor circuit. So, coming to again full half subtractor is a combinational circuit that subtract the 2 bit and produces their difference. So, you have here A B 2 input and you have a typically the difference, we call it difference, and this is a borrow output. So, we call it perform subtraction of 2 bit, one is the minor and another is the subtrahend, and have a 2 input and 2 output. The 2 output is bit D and B 0 represents the difference here, and the output borrow respectively, and the output borrow B 0 is 0 as long as A is greater than B, and it is 1 for A equal to 0 and B equal to 1, and D is the same as the logic for output S for the half adder, that is exclusive OR operation of 2 input, and this is the truth table. You can say here the when you are subtracting A from B, B from A. So, you have getting 0 0 0, here it is you will getting difference also 1 and borrow is also 1, and when you have 1 0, so you will get a difference, but borrow is 0. When you have both, you will have a both 0 virtually. So, this is the truth table you can represent by logic gate. So, B here is a B borrower will be directly only one condition. So, that is your A dash B corresponding to this condition only, and of course, your difference will be corresponding to same as the full adder. So, D equal to A bar B plus A B bar, that is A exclusive B, and this can be represented, difference can be represented by same exclusive OR similar to adder. So, A B with exclusive OR D, and your borrow bit can be represented by A by not and then B and of both like. Now, coming to full subtractor, perform subtraction of 2 bit taking into account borrow of previous adjacent lower bit also, and here 3 inputs are your A B and borrow input denoting the minor, subtrahend and previous borrow respectively, and two output will be difference and borrow, represent the difference and output borrow, and this is the typically you can call it the block diagram representation, where you have a two input. You can call it one is minor and another is subtrahend, and the another third input is your borrow input, and output is the difference and borrow output, and this is the truth table for the same. When you have a 0, then you have a typically borrow input 1, so difference will be your 1 and borrow output will be also 1. When you have a typically 1, so you have again difference output 1 and borrow also 1, because you are subtracting 1 from 0. Here also from you are subtracting from 0 1 and 1. So, you will have a borrow 1, but difference will be 0. Similarly, here you have a 1 and you will have a difference, but your borrow is 0 and 1 0 1. So, you will have a 0 and difference all and 1 1 0 0, and then all 3 1 will become 1 1 here. So, to represent this truth table, typically for subtraction as a difference will be your all these red blocks which represents 1, and this represents the 3 input exclusive OR as we look into the full adder. So, A B I dash, and this is the way how we really are logically solving it and finally getting the D with the exclusive OR A, B and B borrow input. Similarly, we have here the borrow output for all the output, where we have a 1 for borrow output, and then this is the expression we are finalizing, and it comes as exclusive OR with A bar and then ending with this here, and then the taking B I, similarly ending of this and finally ORing for the sum of this. So, this represents it the typically your borrow output. So, this is you can call it the design of your full subtractor difference as well as borrow output. Now, coming to the comparator circuit, a digital or binary comparator are made up from standard AND NOR NOT gate. A comparator compare the digital signal present at their input terminals and produce an output depending upon the condition of those input. And if in its simplest form, a comparator determine if two numbers are equal or in one value is greater or less than the other. So, we have a two input A and B, and we have a n bit comparator. So, we have here the three possible position: A is greater than B, A equal to B and A is less than B, and functional diagram of comparator. Here we can say 1 bit comparator. So, a magnitude of comparator of two 1 bits A and B input will produce the following three output condition when we compare it. So, A equal to B, A is less than B, or A is greater than B and less than B, and this is here 1 bit comparator of A and B. And we can say here if A is less than B, we can represent output X, A equal to B, we can represent Y, and A is greater than B, we can represent Z. And here is a truth table for A B. When we say both are equal, A B are equal, so we will have a typically Y 1, that is the condition for when both are equal, and this is the condition when your A is less than B. So, this is the one only here, and this is the condition when A is greater than B. So, Z is 1 here, and now you can say X, what is the X here? This is 1 only when B is your greater than A. So, this will represent X equal to A bar B, it is represented in logical table, and this is here represented as exclusive or Y equal to A exclusive B, and this Z where A is greater than B. So, this represented Z equal to A B bar, and this is the representation of course by logic gate for three output from two input A and B by taking the NOT, the two A and B NOT here, and then ending with the corresponding function of B, and finally or one goes to directly A, one goes to directly you can call it X, another goes to typically your Z, and this comes as a Y. So, these are the three input like X, Y, Z, and this is the we are using comparator logic circuit for designing for this like. And now coming to 2 bit comparator, a magnitude of comparator of 2 bit A 1 A 0 and B 1 B 0 input will produce the following three output condition when each other, when A 1 A 0 equal to B 1 B 0, or A 1 A 2 is greater than B 1 B 2, or A 1 A 0 is less than B 1 B 2, and these are the typical condition here. And these are the two input A 1 A 0 having a number with the 2 bit, and B 1 B 0 with the another input with the 2 bit, and these are the corresponding output condition of 2 bit comparator. So, for this here we can say A is less than B, A consists of A 1 and A 0, and similarly this is typically if you look into the lookup table, the condition we mention it for all three. So, here we have a condition A less than B, this is A equal to B, and this is A greater than B. So, this is the condition for a less than b, where is the 1, we are taking only those for term. So, these are the condition. Here we are having these condition, and then for a equal to b, we have a typically a equal to b means these where we have a 1, and this is the third condition when a greater than 1, where we have a 1. This is the all these terms like. So, these represent the, you can call it truth table of 2-bit comparator, and this is the logic gate circuit representation of that truth table, where representing a is less than b. A of course, it consists 2-bit as well as b consists of 2-bit, a1 a0, b1 b0, and this is the output which we are getting a equal to b, and this is a greater than b. So, this means you can call it like a, this comparison of 2-bit comparator also can be represented by this logic gate, or we can design by logic gate like also. So, coming to like a multiplexer circuit and demultiplexer circuit, can you tell out like a digital multiplexer is a logic circuit that accepts several digital data input and select one of them at any given time to pass one of the output, and we have a several input like I0 to I n minus 1, that is n input, and we select from this in mux multiplexer and output is 1. So, it depends what is the value of selector, and we select only one out of this. So, this we call it functional diagram of digital mux multiplexer. So, routing of the desired data input to the output is controlled by select input, often referred to as a address input, and the example is a modern home stereo system. A digital muxer is used as data selector, parallel to serial converter, universal gate, and depending upon the input, number of the select lines are used in the multiplexer circuit are classified, and select line are required for 2n input multiplexer, and here you have a select line like a typically 1, 2, 3, 4. So, you have a input possible like a 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. So, these are the possible inputs, and the multiplexer you can multiplex like by typically as a 2 input, 4 input, 8 input or 16 input, and here is the example of your 2 into 1 mux. So, 2 input I0, I1 are selected by using a selector line that A. So, the output is defined as here Z equal to I0 A bar plus I1 A, and what will be the Z here? It depends on what your A select line select 1, then output will be I0, and if you select 1, A value 1, then output will be I1 by this expression. So, with A equal to 0, this expression becomes typically your Z equal to I0 1 plus I1 0, that is I0, and with A equal to 1, this expression becomes Z equal to I0 0 plus I1 1 equal to I1, and with 4 into 1 max. So, 4 input I0, I1, I2, I3 are selected using 2 select line S0 and S1, and the output is defined as Z equal to S typically, because here we are 4 input and these are the 2 selector bit. So, S bar into S1 into I0 plus S0 S1 dash I1 plus S0 S bar S0 bar S1 I2 plus S0 S1 I3, and this is the typically the truth table of it. So, when you have a 0 0 both selector bit, you output is I0. When you have a 0 1, then signal comes output I1, and when you select 1 0, then output is I2. When both input are 1, then you select I3. So, out of 4 only 1 is going to be output depending upon the selector bit. So, now another example is the demultiplexer, in the reverse of multiplexing. So, here you have 1 input and you are distributing to n output depending upon the selector input. So, demultiplexing takes data from a single input line and transfer it to one or more output line, and a digital multiplexer is used as a data distributor and serial to parallel converter, and n select lines are required for 2n output in demultiplexer circuit. So, we have here 1 into 2 demultiplex. So, 1 input I is converted to 2 output y and y0 using a select line here, and the output will be y equal to S I and y1 will be S I. So, here you can clearly see here when selector switch is 1, the output is your typically 1 and 0, and when selector is 1, that is 0 1. So, here depending upon this input is going one time at y0, another to y1 depending on the selector bit. So, coming to like a 1 to 4 selector, one input is converted into 4 output using a 2 selector lines here S0 and S1, and the output will be y0 will be S0 bar S1 bar I, and y1 will be S1 S0 bar I, and y2 will be S1 bar S0 I, and y 3 will be S0, S1, I. So, here you are getting Y1, Y2, I3 or 4 depending upon the S0, S1, I will be going as a output, and this is the truth table that for all combination whether Y1 is typically going I or Y2 I. So, Y0 I or this goes on selector switch of 4 combination, that is the truth table corresponding to that, and it is the example here application of mux and demux. So, for muxing you are selecting one of the input, and demuxing you are selecting any one input to output like. So, these are the example of mux and demux like it is something like that you are connecting like a parallel to serial data and serial to parallel data, and maybe that communication is only through one line. So, there are plenty of example of such can be there in practice like. Now, coming to simplifying logical expression methods, so we have a operator precedence. So, in an expression contains both AND OR operations. The AND operations are performed first unless there are parentheses in the expression, in which case the inside the parenthesis is to be performed first, and the next operation that holds precedence is the complement, and then followed the AND, and finally the OR. The example is f equal to a dot b plus c. So, first AND operation is performed between a and b, and the result of the operation is then ORed with the c. And the famous De Morgan theorem which we are talking about, it is just like a statement of it. So, two of the most important theorems of Boolean algebra were contributed by the great mathematician named De Morgan, and De Morgan theorems are extremely useful for simplifying expression in which a product of sum of variable is inverted. The two theorems here are, first is a b bar equal to a bar plus b bar, and a plus b bar equal to a bar dot b bar. So, this is very important two you can call it two theorems of De Morgan, which really help to simplifying your typically the digital logic circuits like. So, we have a one method of this Venn diagram, we call it method, and this Venn diagram is a graphical representation, so helpful illustration that may be used to visualize the relationship among the variables of Boolean expression is the Venn diagram, and all points inside the circle is belonging to a named variable, and all points outside the circle is not belonging to the circle. So, you can call it all the variables, all the data belonging within the circle is x, and all data belonging within the y, this circle is y, and the outside domain is your typically is correspond to 0 x 0 and y 0. So, you can say circle label x if the points are inside the circle x equal to 1, when outside x equal to 0, and logic gates representation by Venn diagram can be typically here in 4 diagram. So, x and y are binary value in Venn diagram. So, the outside domain is 0 0, where x and y both are 0, and this circle is typically your we say x, this is the circle which x. So, x 0 is this portion, and this is your 0 y, or you can call it your x y bar or x bar y. This is the circle, and this is the common is your x y. So, this is the representation by AND gate. So, AND gate is 1 1 is the AND gate output like of x y, and OR gate is the all three here 1 0 1 1 and 0 0 except leaving 0 0, and of course, here exclusive OR is the typically only the portion which have a typically not consist 1 1, remaining it consists 1 0 and 1 0 1, neither consist of 0 0 nor consist of 1 1. So, these all four different, you can call it like a diagrams represents logic gates like AND, OR and exclusive OR. Now, coming to another method we call Karnatak Map method. This is also graphical method of typically solving the your logical design. So, Karnatak Map, K map in short is called, is a graphical tool used for simplifying a logic equation or to convert a truth table into a corresponding logic circuit in a simple or orderly process. Although a K map can be used for problem involving any number of input variables, in practice, in practical usefulness is limited to 5 or 6 variables, and the K map like a truth table is a means of solving the relationship between logic input and desired output, and Karnatak maps are powerful, widely used tabular method of logic simplification that are used to find the simplest sum of product or product of sum, and each cell in the Karnatak map correspond to one particular input state that in the truth table. And step to simplify a logic expression using Karnatak map are the draw the empty Karnatak map, the second is fill 1 and 0 into corresponding cells using the original logic expression or its truth table. Identify and draw the loops on the Karnatak map to group together adjacent ones or in bracket for sum of product or adjacent zeros for product of sum, and 4 is create the expression for each group and combine to give the simplified logic expression. Now, the first is create the empty Karnatak map. The number of n input define the number of cells into n in the Karnatak map to be drawn, and for example, for two variables a and b there are 4 possible input state, for example 0 0 0 1 1 1 1 and 1 0. Hence, the Karnatak will have a 4 cell, each cell corresponding to the one particular input state, and the small numbers in the top left corner of each cell. So, the decimal equivalent of the binary input code for that cell, and notice that the cells are arranged such that only one bit changes when we go to the adjacent cell, and each cell thus correspond to one particular minterm m I or max term capital M I, where I the decimal equivalent denoting the cell. So, here typical example is the two variable Karnatak map. Here we have a Karnatak map between A and B, and A B can be have a 0 1 and B also can have a 0 1, and these are the corresponding to the combination like A bar B bar 0 1 2 3. I mean, this is typical representation of exactly the same of 4 combination here, I mean of A and B, and output of course we have 2, and here it is 0 0, that is 0 1, that is 0 1 to typically 1 0, that is 0 1 0 to 2 10, and this is 1 1 equivalent to 3 on the base of 10. So, truth table of 2 variables for this Karnatak, this is a Karnatak map we call it, and now 3 variable Karnatak map for each cell. Here it is typically A B C. I mean, the typical example is of your B A here and C here. So, you have a B A, first is the B and then A, all these, and this is the your C. So, if we say this is typically the Karnatak corresponding to 0 1 2 3 and 2 4 5 6 7 6, or you can represent the 3 variable Karnatak map in this form also. You can take C B here and A you can take here. So, this represent 0 1 2 3 and 6 7 4 5. I mean, this is the, you can call it the binary code, you can make a representation in this manner for 3 input, 3 binary input like. So, this represents the typically Karnatak map. So, for 4 variable Karnatak map A B C D, and these are the binary code. So, here binary code, here we have a variable A B and here we have a DC. So, you can have a 0 1 2 up to typically 15, because there are 16 combination for 4 variables like I mean here. So, that is F equal to F A B C D. So, second is the filling the Karnatak map. Each cell of Karnatak map is filled with the either a 1 or 0 signifying the output for the input corresponding to that cell, and the originally binary function which needs to be simplified may be provided in any one of the following form, and by specifying the binary decimal number that corresponds to 1, output 1 sum of midterm, or output 0 that is product of max term, and a general logical or Boolean expression, a truth table. So, typically map the following standard sum of product expression on a Karnatak map. So, these are the term, and these term you can, all terms represents the corresponding to, you can call it the one midterm. So, you can represent this all midterm by different here 0 0 1 1 A bar B bar C bar, and these are the midterm which you can place here on this Karnatak map as a first midterm is itself 3. So, you can have a here 0 0, this represents 0, typically this 0 0 and that is 0 1. So, that is typically corresponding to this expression is corresponding to this. Similarly, you have a mapping of all these midterm on the by 1 1 1, and this represents sum of midterm of 3 4 13 15 12 1 and 10 corresponding to this, and fill 1 into the cell corresponding to the above input, and rest of the cell have a 0, I mean which we are not pointing here. Now, map the following standard POS expression in the Karnatak map. So, here typically the given expression, these are the sum of the product. So, you can have a again product of this all max term, and this is we call it capital M max term 12 13 2 15 and 3 by representing these all expression, and we write a 0 in all the boxes which represents this your corresponding to this max term here. So, all fill all zeros into the cell corresponding to above input, and rest of the cell will have output equal to 1 which we are not putting here. So, that is the way how really product of sum we are presenting in the Karnatak VK map or this Karnatak map. Now, creating groups in Karnatak map, when all the output are entered all 1 or all 0 depending upon the sum of product or product sum forms in the final required respectively, and must be grouped together according to the following two rules. Each group must contain 2 to power n adjacent cell, where n is the positive integer, and each group should be made as large as possible while satisfying the constraint of having cell numbering power of 2. So, larger the group form, the simpler will be the final function. So, each cell with 1 or each cell of output for either for sum of product or product sum must be included in at least in one group, and the group may overlap. So, one cell may be included in several groups, but any group that has all its element included in another group can be ignored, and these may be several correct minimal form for a given logic function dependent upon the particular grouping that are chosen. Means there can be many solutions for one problem like. So, once the group have been assigned, a logic expression can be created for each group. Write down the common input like AND product of the terms if 1 or sum of the terms if using 0 that describe the specific group, and combine accordingly sum of product or product of sum. So, depending upon the looping, the combination of adjacent square that is useful during the simplification process represent the number of variables in output, and 1 square represents the 1 midterm giving a term of 4 literal, and 2 adjacent square represent the 3 literal, and 4 adjacent square represent the 2 literal, and 8 adjacent represent 1 literal, and 16 adjacent in 4 by 4 represent the 1. So, simplify the typically f equal to 3 midterm a bar b c bar plus a b c bar plus a b c into simpler SOP form of the Karnatak map. So, here it is typically you can call it, we are putting all in this Karnatak map of 8, we are putting all the 3 terms here, the 3, and now to simplify it we can combine in this manner. So, this combination will typically give us this combination give a b, because c is cancel out because it is passing in the c plus c bar, and the second combination of course, c is not there. So, and c is with the here typically with the c bar only, and this is corresponding to b, a is cancel out here only b. So, it is called b c bar. So, that is the representation. So, we are simplifying this with the help of Karnatak map, I mean this a large expression in the minimal form, which we can represent by logic gates like. So, another concept here is the do not care conditions. So, sometimes a situation arises in which some of the input variable combination are not allowed. For example, in a particular coding scheme with 4 input bits called BCD, there are 6 invalid combination like starting from 1010, or you can call it typically A to F combination in equivalent to hex code. So, since these or 10 to 15, and since these unallowed states will never occur in that particular application. So, they can be treated as do not care terms, and with respect to their effect on the output. So, that is for do not care term, either 1 or 0 may be assigned to these output, and it really does not matter since they will never occur. So, you can use for simplifying them. So, do not care terms can be used to our advantage on the Karnatak map for further simplifying the Boolean expression for particular application, and for each do not care term and x is placed in the cell. When grouping the 1, sum of x can be treated as 1 to make the large grouping, while other can be treated as 0. They cannot be used as vice versa if we grouping zeros. The larger a group, the simpler can be resulting will be 0. So, this is the typically do not care conditions. So, you have a 6 in BCD code, and these are the 6 do not care terms. So, all x representing here do not care, and these are the only output valid output here. So, this expression we can represent first combination as a combining 2, it is only a b bar c, and second combination only one term a bar b c d bar, and of course, this can be representing both sum of both. So, a b bar c bar plus a bar b c d, and this can be of course, if we use the do not care term, we can have a 1 and 2 combination of that. So, 1 comes only a and 2 comes b c d. So, the y comes a plus b c d. In place of this is the short form which we are getting from this Karnatak map, and certainly it will need a less logic gates with less. So, here also in product of sum form on the same we have a valid output only this, the remaining are of course 0. So, we take a 0 here and these are do not care term. So, if we take only all typically here, so here it is one combination is corresponding to a 4. So, that is a plus c, and 2 combination again of 2, that is a plus b, that is second combination. Third combination is of consist of 2 only. So, a c bar d, and it comes by a plus b multiplied bracket a plus b parenthesis a plus c bar d, and this can be reduced if we use the do not care as a combination. We have to only solve for 0, but we can take advantage of x. So, this is a one combination which consists 4 variable, this is also 4 and this is also 4. So, term goes, one goes a plus b, a plus c, 2 goes a plus c b, and third goes c bar d, and now we have a y in bracket a plus c and bracket a plus b and bracket c bar d. So, this is the short form in compared to the previous expression where we are taking do not care term for solution of it. Now, we have some theoretical problems. So, list the 2 advantages of simplification. The solution is smaller, less expensive to build circuit, and maintain uniform propagation delay for all logic circuits. How many data select line are required for selecting 8 bit, that is only 3 channel, and the simplest equation which is present on Karnatak map. So, that is typically only taking 1. So, this is a combination of 4 and 2, that is x equal to a c, this represent 2 combination, and b represent the this combination of 4. What is the gate best suited for basic comparator, that is x4, and the device shown in most likely be here it is typically demultiplexer. And what is the expression for carry in full order, we already discussed it. Carry C0 carry output is B C I plus A exclusive or B with C I. Solve the network for figure given here. For this we have a typically the expression first for the first bracket a plus b, then multiplied with the AND gate of C, and then ORing the another D with this. So, this is the logical expression for those networks shown here. Then you have a typically what is the logic representation for the figure shown here, this represent x NOR. Now, coming to the solved problems. So, using the Boolean algebra technique, simplify the expression f equal to a b plus a in bracket b c plus b in bracket b c. So, the solution is we can expand this expression, typically all midterm we can have putting like along with the a we have a b c. So, we can represent it in the adding the same variable here, and finally, we are coming to typically simplifying it, it comes like a c plus b 1, that comes a c plus b. So, in place of this expression is by these logic gates, and which we simplified it into a c plus b, this is by this logic gate. So, you can see in place of 5 logic gate, it can be represented only by 2 logic gates here. So, that is the advantage of this typically simplifying the expression of by Boolean algebra. So, minimize the following Boolean functions using the algebraic manipulation. So, these are the typical terms. So, you can simplify it by same De Morgan theorems or other expression, and finally, this expression come in this short form, this big expression by simplifying it. Applying the De Morgan theorem for following. So, I mean the typically when you really break into, first you will be using corresponding to the in between, this is the expression, and you can break it to first. So, it comes this plus become dot, and then you break the double. So, it becomes only this one, and this also d bar with this expression comes here, and then you can remove double bar. So, it comes a plus b c bar multiplied in bracket d bar plus e plus f dash. So, this is the after applying the De Morgan theorem, the function comes finally. So, applying again De Morgan theorems to this. So, taking this, so you take this as a bar, so it comes bar a b dot c bar d bar, then e f bar, and then again you can open expression of this, and finally, it comes into simplified as a, you can call it some product of sums like. So, draw the circuit to implement this f equal to a dot b bar plus a dot c bar and whole bar of it, simplifying this function and redraw the. So, we can have this expression itself, I mean drawing this circuit corresponding to this, and when we simplified it by De Morgan theorem, it comes like f equal to a b. So, it is just representing by 3 input AND gate. So, that is the advantage of this simplifying by De Morgan theorem. The application of De Morgan theorem virtually reducing the number of logic gate. So, here you have 3 logic gates, and with the propagation double propagation delay is a single logic gate with the only reduce half the propagation delay. So, coming to the express the Boolean function f equal to a plus b bar c, a sum of midterm. The first midterm is missing. So, you have to put like a typically along with here typically a plus that is again 1. So, you can have a can be presented here. So, you put the value here and it comes the typically the kind of 4 term. So, second term is missing for a, that also you put it, and finally, this comes the expression in this form, which we can represent in a mid term m 7, m 6, m 5, m 4 and m 1, this total expression, and in short form it can be presented FCD as a sum of 1 4 and 4 in finally, it can be in form of this like. So, convert the following Boolean expression in standard form. So, for the POS product of sum of ABCD, take the term at it one at a time. So, we take this first term and D is missing. So, we add the D here, D bar, and this becomes typically this 2 expression, then take a second term, that also typically we are using kind of this kind of De Morgan concept. So, second term we again here A is missing. So, we add the A bar and simplified this, and then third term here is directly there. So, we can just add all these terms. So, final comes as a you can call it sum of the product form, final form of this simplified form. So, coming to example 8, simplified f equal to max this min term of 1 2 3 6 into sum of products using Karnatak map. So, putting all 4 min term on this Karnatak map with the 1 1. So, you have a group 1 of the 2, that is A bar C, and second group is B C bar. So, expression comes typically A bar C plus B C bar for solving this like, otherwise it is a 4 term you can write separately. So, similarly, you have a 4 by 4, you have a so many, I mean the midterm equal to your summation of 2 3 4 5 7 8 10 13 15. So, you are mapping all these 1 for all midterm, and now you are combining in different groups, like a typical example of group of 2, group of 4, group of 2, and only 1. This group can be combined with the typically with the group of this and group of this. So, corner can be combined. So, this with this and this with this, these 2, these 4 and these 2. So, these are all typically 8 midterm can be expressed like as a first group, that is of 4, that is B D, second group, I mean this is the second group, that is A bar B, A bar, that is corresponding to, and B into C. So, D is cancel out here. Similarly, for third group B bar C D bar, and fourth group A B bar D bar, and you can add all together, that represents the virtually the simplified form of so many terms here finally. Now, you simplified the midterm again for f equal to 0, 0, 5, 7, 8, 10, 12, 14, 15. So, you map on this and you combine it now. The one combination can be of this to this, that is first the combination comes of the typically of these 2, then the combination of typically of combination of these 2 and this one, and typically you can call it these 2, or can be even a combination with this. So, all these groups we can call it the starting group 1, this presented by A bar B C, second group is A B C, A B C, that is the group here. So, here you can call it C and D are here. So, D is cancel out. So, but this is A B and C is added with that, that is A B C. Similarly, for all 4 group, and you have a final expression, I mean typically of taking odd midterm, you can have a f equal to summation of all these 4 group, which can be simplified into the finally in the group form, reducing the variable. So, here also you have a midterm, similar example A B C D. So, you have some midterm present the 1. So, all 4 can be combined together, and these 4 can be combined together. In place of writing so many, you will have a just group of 4 4. So, it will be B D and B bar D. So, minimum sum of form will be B D plus B bar D bar. Similarly, 12th example, Karnatak map to minimize the product of sum. So, these are the different product sum. So, these are all mixed terms. So, max terms are represented by 0 here, we are putting here. So, these 4 can be combined into 1, because C is cancel out here. So, it becomes only, and A is also, because it appears in A and bar. So, it also sorry B and B bar. So, it comes only A, and then second is combination of both. So, here it only with the C, and typically A is also cancel out. So, B bar plus C, and the final expression comes f equal to A in bracket B bar C, that is in product of sum form. That is only, that is the reason we are taking only the 0 here. So, coming to the example 3, map the following sum of product on the Karnatak map, A bar plus A B bar plus A B C bar. So, we are just putting first A here. So, A is represented virtually, you can call it like a entire A is corresponding to the these two term, sorry, A bar is represented these two term, A B bar is represented by, you can call it these two term, and A B. So, A B is corresponding to this, A B corresponding to this, and C bar is this. So, this is representing this term like. So, this is the all one, I mean, so you can have all this in terms of your this expression here, you can just present it, or you can call it A bar can be presented in terms of, because B are missing. So, you have to put B and C here, and this comes 4 min term, and the second term represented of this also typically can be form of this. So, second term of sum of product can be this, and third term, I mean, present is taken as it is, and now you have all terms corresponding to all one here, and that is you can call it sum of M 3 2 1 0 5 4 6 like. So, example 14, map the following product of sum on a Karnatak map. So, here we are putting on this 3 variable Karnatak map, all these max term, I mean, correspond to these typically here, and then we can write the sum of all max term here correspond to this like. So, now there are some unsolved example which you can do in the similar manner, I mean, just for the purpose of exercise, and these are the references by which we have developed this lecture, and thank you.